Okay, I'll do it. Okay, so we can start. So welcome everybody for the webinar of today. The speaker of today is Mickaël Bourgoin, and he will talk about Lagrangian investigation of diffusion and entrainment in a self-similar turbulent jet. As usual, I introduce the speaker and then I leave him the stage. So Mickaël Bourgoin got his PhD on dynamo effect and magnetohydrodynamic in Lyon in 2003. He spent 1 year as a postdoc in Cornell University, where he studied several Lagrangian aspects of turbulence before being appointed as a CNRS researcher at LEGI in Grenoble in 2004 to investigate the interaction between inertial particles and turbulence. At present, he is CNRS research director in the physics laboratory at École Normale Supérieure de Lyon, where he carries investigations on fundamental turbulence, particle-laden flows, and granular media, among other topics. He is also director of the French National Research Network GDR, Navier-Stokes 2.0, and teaches advanced fluid mechanics at École Normale Supérieure de Lyon and École Centrale de Lille. So it's with great pleasure that we host Mickaël Bourgoin for the webinar of today. So Mickaël, I stop sharing my screen and you can start sharing yours.
Okay. Where is it? Where did it go? Oh, seems the presentation disappeared. Sorry. Up.
So,
wait, do you see the? No, you don't see it, right?
Not yet, not yet. So probably when you need to stop sharing and start sharing once again.
Yeah, start again. Okay. So now.
There we
go.
go.
You see it?
Yes.
Okay. Thank you. Okay, thank you very much, Francesco, for the introduction, and I also wanted to thank you for inviting me to give this this seminar. And well, not only for inviting me, also thank you and all the lab in Lille, LMFL, for setting up this very nice series of webinars. I think it's very helpful to keep the community tight in this complicated period. So thank you so much. So I will present you today some recent work we have been doing on the Lagrangian investigation of a turbulent jet, and focusing more precisely on the properties of particles dispersion, particle diffusion, and also the role of entrainment in understanding how particles diffuse and are dispersed in a turbulent jet. So this work is a collaboration with many persons that you see here, and I would like mostly to highlight the amazing work that was done by Bianca Vigiano and Thomas Basset, who are two PhD students working on this project. And I mean, without them, all what I am about to tell you just wouldn't exist. So thank you so much, Bianca and Thomas, for this very nice work you have been doing. So what is this about? This is what we'll be studying. Basically, this is the object we'll be studying. It's a jet. So you can see it's a jet that is injected here. You can see the nozzle, and oops. Is it still sharing, or did the shares?
The shares stop.
Okay, I don't know what happened. I don't know what happened there. Something. Okay,
there you go. We see it once again.
Okay, sorry about that. So you can see here the jet. So we see the jet with some small tracer particles that you can see here dispersing from the jet, and of course the jet is surrounded by some fluid that is not tagged, so you don't see it, but there is fluid at rest here on the sides of the jet. So what we'll be investigating is how these particles disperse in the jet. So of course, jets has been studied for many years now. So the new thing that we'll bring here is some new insight and some prospect on the Lagrangian approach of the jet. And as we will be discussing, the Lagrangian approach is very relevant when you address transport properties of such turbulent flows. So that's what we will be discussing today. So why were we interested in this problem? So for, I would say, several reasons. Many of them were just fundamental aspects. The idea is that a lot is known on transport and turbulence, on homogeneous, isotropic, and stationary flows, but much less is known when in realistic conditions for the flows deviate from this, let's say, ideal playground of homogeneous isotropic turbulence. And the jet is a sort of canonical, non-homogeneous, non-isotropic, and non-stationary flow that is well documented, at least from the Eulerian point of view. So it was a nice starting point to go forward and investigate these transport properties and the Lagrangian aspects of turbulence in such non-homogeneous flows, taking this jet as a canonical, well-documented flow. It is, of course, very important for applications because jet-like flows exist in a wide range of applications in human activities like sprays, injectors, mixers. Here you have an example, okay, very relevant for this period of pandemics. Sneezing is also like a jet-like flows, and there are also a lot of natural flows which resemble jet-like dynamics. So, okay, these are the motivations. And how are we investigating this system? Well, we are interested in the Lagrangian dynamics of the particle, so we perform Lagrangian particle tracking experiments. To do that, we use this device. So this device was originally developed in our lab for Lagrangian studies, but in homogeneous flows. We call it the LEM, the Lagrangian exploration module. Is a icosahedron. Originally, it had a set of 12 impellers to force a flow in a relatively homogeneous and isotropic manner. So we're not using the impellers here. We're just using this vessel because it's very convenient for optical access, illumination, and taking movies with multiple cameras. But we'll be injecting a jet from below, and the jet will be formed here in the center of the vessel and then pumped out from the top of the vessel. And we'll be taking movies of this jet, and we see the jet only in the nozzle, and then we record the trajectories of the particles. I will briefly mention a bit later how we reconstruct these trajectories. So that's how we will do it. And the questions I would like to address today, more specifically, are two questions. So I hope I will be able to discuss two of them. As I was preparing the slides, I realized that maybe the first point will already take me most of the time of the talk. So I will see if I can also discuss the second point. But the first point that I would like to address is, can we extend Taylor's theory of turbulent diffusion, which is a theory that Taylor developed in 1922 in the case of homogeneous and stationary turbulence? Can we extend this to the case of non-homogeneous flows as the jet? We will see that Batchelor in 1957 proposed a way to extend Taylor's theory. With our experiments, we would like to test how relevant this approach that Batchelor proposed is when you address this question in a real jet. And the second point that I would like to discuss is what is the role now of entrainment. So this part of the flow that you are not seeing here in the movie, so the particles that are in the quiescent flow, in the quiescent part of the flow surrounding the jet, which are entrained into the core of the jet and to form the global dynamics of the jet. So what is the role of this entrainment of particles to the overall diffusion and dispersion of the particles that are seeded here into the jet? And we'll see that this can be interpreted as a Lagrangian effective compressibility effect. And this will also allow us to build a direct connection between what would be a turbulent diffusivity and the entrainment mechanism. So, okay, let me start with the first point about how to extend Taylor's theory to the case of turbulent jets. So let me briefly remind you what the Taylor theory is for diffusion of particles, turbulent diffusion of particles. So this is a work that was done by Taylor in a celebrated paper in 1922. And in this article, what Taylor showed is that if you're interested in the growth rate of a cloud of particles that are ejected in a source point in a turbulent flow, so this is sketched here, so the turbulence is sketched by this noisy background that you see. Turbulence is supposed in this work to be homogeneous, isotropic, and stationary. Stationary is a crucial point in Taylor theory. And then you have a source point here where particles are emitted. So these are passive tracers, could be a passive scalar that is transported and then mixed by the turbulence. And Taylor theory the main result is known as the Taylor Theorem, which is written here, and it directly connects the mean square displacement of the particles, which tells you how fast the cloud of particles is growing. And it tells you that this is directly related to the Lagrangian correlation function of the velocity of the background turbulence. So here, RUU is the correlation function of the velocity u, and this is the Lagrangian velocity taken along the trajectories of the particles. So it's a Lagrangian correlation function, where you define the velocity u at a given time and the velocity u at a time shifted by t0 plus tau. You take the product and then you define the correlation function, the Lagrangian correlation function of the velocity here. So we have this very simple relation here, what tells you that you can simply predict how a cloud of particles grow if you just know a very simple Lagrangian statistics of your surrounding turbulence, which is this Lagrangian autocorrelation function. So as a matter of fact, this is the fluid mechanics point of view of a much more general theorem in random signal analysis, which relates the correlation function of the derivative of a quantity to the second derivative of the correlation function of the quantity itself. But that's how Taylor basically wrote it. So this is a very nice theorem that connects the dispersion properties of the mix and the transport properties to the Lagrangian properties of the underlying turbulence. Depending on what you prefer, you can write it with the correlation function, but correlation function is also trivially related to this other quantity here, which is the Strato function, the Lagrangian Strato function, which is related not to the product of the velocity at 2 different times, but to the difference of the velocity at 2 different times. And it is also trivially related by a simple Fourier transform to the Lagrangian spectrum. So depending on which quantity you measure or you prefer, you can write this theorem using correlation function, Strato function, or Lagrangian spectrum. So, okay, so this theorem is very useful because it allows you to simply relate this simple quantity, which is the Lagrangian correlation function of the velocity, to the mean square displacement of the particles, so how particles grow. And if you really want to extract this quantity, so the mean square displacement, so you need to have a nice description of this Lagrangian correlation function, which is something that you can get either from measurements, you can get it from direct numerical simulations, or you can get it from stochastic models. As a matter of fact, there are certain regimes here for the mean square displacement, which can be trivially derived, even if you don't know the exact shape of the Lagrangian correlation function, and in particular, in the limit of very small timescales. So in very small timescales, you will have here a ballistic regime, mainly because the displacement of the particles at short timescale by a simple Taylor expansion is a velocity multiplied by time. So the mean square displacement then is velocity squared, the variance of the velocity multiplied by t squared. So this is a trivial regime. And for the long time regime, if you use the Taylor theorem, which I recall here, you can define this integral when t goes to infinity. This defines what we call the Lagrangian correlation timescale TL, which is here. So in that case, you see that the first derivative of the mean square displacement is simply sigma u squared times TL. You integrate it once, and you get this regime where the mean square displacement grows linearly with time, and this is a diffusive regime. And that was probably the main result of Taylor at that time, is that in the long time limit, turbulence behaves as a diffusive process with this turbulent diffusivity that is related to the fluctuating velocity and the Lagrangian correlation timescale. But now, if you want to have a more complete description of this phenomena, you will need to know not only these asymptotic regimes, but to know the detailed description of this correlation function. And so, as I was saying, you can measure it. You can measure it in experiments, in simulations. You can do modeling. Simplest models can be purely phenomenological. For instance, you can build this correlation by pieces, by noting that in the small scales, you can have some trivial regime here, where this should behave as a parabola if you have a system that is differentiable and stationary. Then you will have in the intermediate regime, in the inertial range of scales of turbulence, you can use, for instance, Kolmogorov phenomenology to derive some law here where correlation function should be linear in time, and then it should decay exponentially with time here. But then you can also use some more sophisticated description of this, for instance, using stochastic modeling. And this has been done, for instance, by Sofford in 1991, by extending some classical Lagrangian stochastic models, which is the random walk or the Langevin model. So Sofford proposed a more sophisticated model where the dynamics of the particles is modeled based on the acceleration, which is a random process in this approach. This is very nice because this model gives you a very simple expression, analytical expression for the correlation function here, RUU, as a simple double exponential with two characteristic timescales. One that is characteristic of the dissipation timescale of the turbulence, the other one that is characteristic of the large scale of the turbulence. Usually that's the minimum ingredients you want for a model of turbulence to have at least two timescales so that you can define dissipation, inertial range, and large scales. And these two timescales in the context of these models can be simply related to classical Eulerian quantities as the dissipation scale or the integral Eulerian scale, accounting to the knowledge of two important constants, which are C0 and A0, which are constants that characterize the inertial range dynamics and the dissipative dynamics of the particles. So these models have become quite popular because they allow you to get this simple expression for the correlation function, and then to address this problem of particle dispersion and particle diffusion using the very simple Taylor theorem. And what is nice with these models is that you only need to know two parameters, which are C0 and A0, and then you can build RUU. And based on that, if you know the properties of the turbulence, essentially if you know epsilon, so the dissipation of the turbulence, then that's sufficient to know, if you know that particles are injected at a given point, to know how this cloud of particles will grow by simply integrating the Taylor theorem. Okay, so this is not okay. This is just to say that these quantities C0 and A0 for the case of homogeneous isotropic turbulence have been extensively studied, and we know they depend on the Reynolds number, but we have reasonable estimates in the case of high Reynolds numbers to know these quantities. So this is nice because then we have this nice tool, and we can almost say that the problem of particles diffusion for homogeneous isotropic turbulence is solved. It is solved in the sense that we can build very simple models with the minimal ingredients that will allow to predict how a cloud of particles grow due to turbulence. Now the problem is if you have a flow that is non-homogeneous, and like a jet, for instance, that I will discuss in a minute, if it is non-homogeneous in space, then it will be non-stationary from the Lagrangian point of view. And the fact that we lose these stationarity properties makes that this Taylor theorem is not valid anymore. So we cannot extend trivially this result from Taylor to the case of more realistic flows where the turbulence will not be homogeneous and isotropic. So let's take, for instance, the example of the jet. Here, what I have represented, so in the background is what would be the a picture of what the background Eulerian fluctuations are for the jet. And here in orange, I just sketched what would be a trajectory of a particle that was released here at the nozzle of the jet. And you see that different positions of the jet, the statistics, the Eulerian statistics of the turbulence will evolve. And as a consequence, as the particle is moving along the jet, its Lagrangian dynamics at different timescales will be different. So in this situation, you see that the Eulerian inhomogeneity of the jet for this particle along these trajectories results in a non-stationary Lagrangian dynamics. So for this reason, we cannot apply the Taylor theorem because the Lagrangian stationarity is a strong hypothesis of this theorem. So the question is, can we extend the derivation of this theorem to the case of non-homogeneous in the Eulerian sense flows and non-stationary in the Lagrangian sense flows? And this was such an extension was proposed by Batchelor. So you have his picture here in 1957, where he derived an extension of Taylor theorem for the case of non-homogeneous but self-similar flows. So self-similarity is one of the properties of the jet. So what does self-similarity mean here? So it means that if you can rescale the Eulerian fields of different quantities, velocities, typical scales, concentration profiles. So you can rescale them simply by the value along the center line here, u0z. So if I take the example here of the actual velocity, so these profiles here represent a sketch of the profile of the actual velocity at different z locations downstream the jet. So this being self-similar means that if you rescale these profiles by u0z, which is simply the value at different z positions but along the center line, then the rescaled profiles are only dependent here, that will be this quantity f of theta, it's the profile ue divided by u0, depends on a single self-similar variable eta, which is the radial variable r divided by some geometrical variables, which can be either the half width of the jet or the streamwise distance z, because in the case of the jet here, r1/2 and z grow together. They are proportional, meaning that the jet is expanding as a linear cone. So in the self-similarity can be seen here. So these are the raw profiles. So here in purple you have the profile. In blue you have the profile of the streamwise velocity at a given distance from the nozzle. In this case, is in our experiments that's at 10 centimeters. Then as you move downstream, you see that the profile is evolving. But now if you rescale this profile by the center line value u0 of z, which is simply the value given here at the center line where r equal to 0, if you rescale it by this quantity and you plot it not as a function of r but as a function of eta, which in our case will be r divided by z, you see that all the profiles collapse. So that's what we mean by self-similarity. And moreover, in this and such self-similarity usually applies to a whole set of variables, which can be the mean field, also the RMS, the standard deviation of the velocity, but it also applies to the scales. This is LE, is the Eulerian correlation scale of the flow. It also applies to the dissipation rate. So most of the usual variables that characterizes the turbulence have this self-similar property in this sort of jets. And besides these quantities, the center line quantities like u0, sigma u0, etc., tend to follow power laws in the sense that they depend on some power of z, z being again the streamwise distance to the nozzle where the particles have been injected. So, and sometimes you can have a virtual origin z0, but if you shift z to the z virtual origin, you have some power law dependence of these center line quantities, and this is very well verified in our jet and in jets usually. For instance, sigma uz, so the standard deviation of the velocity along the center line decays as 1 over z. The Lagrangian scale grows as z, so this is apparent by the fact that the jet is expanding as you move in the streamwise direction. The dissipation rate decays as e to the -4, and so on. So you have a lot of these laws which characterize the self-similar decay of the jet in the streamwise direction. So with this, in this range of approximation, with this sort of self-similar behavior, Batchelor extended the Taylor hypothesis, showing that if you define now these stationarized variables, so instead of using the Lagrangian velocity, the raw Lagrangian velocity u along the trajectory of the particles, you define this stationarized velocity. So meaning that u at a given time here, will be the actual velocity of the particle to which you subtract the local value of the Eulerian field at the position of the particle, and you normalize it by the variance of the fluctuations at the position of the particle along its track. So this is a stationarized velocity, and then you also stationarize the time by simply considering the time scale normalized by the local Eulerian time scale. So here you see that this is the Eulerian profiles are non-homogeneous, UE, sigma UE, TE, because of the properties of the jet that is decaying in space. And by doing this, you define this new set of variables, which the idea of Bachelor was to define quantities that will behave as if they were stationary, and in that case, being able to use the Taylor theorem for these corrected variables. So this is what is done in this paper by Bachelor, and there he shows that indeed this stationarization works if you have a self-similar jet with this power law decays in the central line. And in that case, the stationarized Lagrangian velocity here, the stationarized velocity here has a Lagrangian correlation function that is stationarized in the sense that then it is independent on the position of the jet, and hence it is independent on the time along the particle track. And when you do that, this property, Bachelor defined it as the Lagrangian self-similarity. And the idea is that if you have this Lagrangian self-similarity, then you can extend Taylor theorem to the case of non-homogeneous and non-stationary flows. So what we wanted to do here in this work was to test whether this idea of Lagrangian self-similarity holds in an experimental free-shear jet, what was not tested since Bachelor. And then if it is relevant, if it works, then can we characterize these stationarized Lagrangian dynamics of the particles in the jets? Meaning, can we then fully characterize this correlation function, stationarized correlation function RUU? For instance, does it fulfill the same shape that can be predicted from these simple stochastic models that I was telling you as double exponentials? And in that case, if that works, that means that we only need these two constants, C naught and A naught, that I briefly mentioned earlier, to characterize this stationarized correlation function and then be able to extend this Taylor theory to understand how particles disperse in these non-homogeneous flows. So that's what we wanted to do. So to do that, we performed these experiments in this setup that I was telling you. So some more details. We have a jet with a 4 mm nozzle. The Reynolds number was a bit varied, but I will discuss mostly today only one Reynolds number, which is which experiments were carried. So at R lambda 230, that corresponds to a Reynolds number at the exit of the jet of about 28,000. We consider small polystyrene, it was polyethylene particles, 250 microns in diameter, almost neutrally buoyant. Experiments are carried in water, so the particles are almost neutrally buoyant. The idea was to have tracers, particles that behave as close as possible as tracers. And we will see that 250 microns is fine for certain statistics, but probably not for the smallest scales that we would like to resolve. And we perform Lagrangian particle tracking here using a set of 3 high-speed cameras operating at 6,000 frames per second with a resolution of about 1 megapixels and some simple panel backlight illumination with panel LEDs facing the cameras. So when you do that, typically that's how one movie looks. You have these movies from the 3 cameras. You use classical algorithms to detect the center of the particles, center match, using some calibration that I will not detail, and then you do the tracking. And that's the kind of trajectories that you record. I only put here very few, just so that you can see the trajectories. But overall, we are able to reconstruct more than several millions of tracks, which give us a lot of statistics to make these studies. It's important to have a lot of statistics because here we will need to condition the statistics to the position z along the particles, because we want to test this Lagrangian self-similarity, which requires to test the statistics at different z locations downstream the jet. So if you put all the trajectories together, you get this nice shape of the jet that you can see here. And you see that most of the particles are indeed injected at nozzle, and we have some spurious particles which are here, which are some particles that remain in the quiescent part of the flow and that are entrained in the jet. So these are a few particles which are statistically not relevant, but that still shows you this entrainment phenomena that I hope I will be able to discuss later on. So now if we want to apply these stationarization formulas by Bachelor, we need then to have access to a certain number of fields. We need to know the field of the mean velocity, the mean Eulerian velocity. We need the field of the standard deviation of velocity. And we also need the field of the Eulerian timescale TE here. So, okay, what is shown in this panel here is the mean field UE, which we directly get from these tracks by simply binning space, and you measure the velocity in the bins. So we have so many tracks that we have a very well resolved mean field. Same thing for the standard deviations. Here we do the same thing. You bin space, and you measure the standard deviation of the velocity at every position. We assume axis symmetry of the jet. So here all these fields are averaged in the azimuthal direction, and you can do that for the different components of the velocity. So based on these two fields that we measure, the mean field and the standard deviation field, we can easily connect. Then we have here the Lagrangian tracks, to which we subtract the mean field here, and we divide them by the standard deviation, and then we get this stationarized Lagrangian velocity along the tracks, which is corrected by these two fields. What is a little bit subtler is the time scale. So for the time scale, to access this corrected time scale proposed by Bachelor, we need to have access to the local Eulerian time scale of the flow. So to do that, what we need to do is to have a measure of the Eulerian autocorrelation of the flow at different locations in the downstream direction. So to do that, we condition statistics on small disks at different location Z to the nozzle. So here the distances are given in terms of nozzle diameters. So this is as 15 nozzle diameters up to 45 nozzle diameters. So typically, usually the self-similar regimes is well defined for this region here. This one is still in the near field regime of the nozzle, for which self-similarity is known not to hold so well. But I will still plot the values for these different locations. So what is plotted here is the Eulerian correlation function. So Eulerian meaning that we plot the correlation function of the Eulerian field as a function of separation here calculated within this disk. So at a given Z position, but separation is taken in the transverse direction. So you see that we have this correlation that decays to 0, and then we define the correlation length as the integral of this Eulerian correlation function, and then we define the Eulerian correlation timescale simply as the ratio of the Eulerian correlation length divided by the local value of the standard deviation of the velocity. Okay, so now we have TE, and since we have TE, we can define the stationarized timescale T tilde a la Bachelor. Since we are doing this Eulerian analysis, it is also interesting to measure epsilon, the dissipation scale. So we do it in the similar way as we did for the correlation function. It's a 2-point statistics, but we use now the Strato function S2, which is defined here. And we use the scaling in inertial range for S2, which according to classical Kolmogorov scaling should go as delta R to the 2/3. So by plotting here S2 compensated by delta R with the appropriate power and with the appropriate constants, we can measure the value of epsilon at the different locations downstream the jet. So once we do all this Eulerian analysis, we get these very nice trends where the fields, the mean field along the center line here decays as 1/Z. So do the fluctuating velocity sigma u, the standard deviation of the velocity. The Lagrangian scale grows linearly with Z. Epsilon, which is proportional to sigma cubed to LE dimensionally, decreases as Z to the -4. And the time scale TE grows as Z squared. So I just put here some plots that show these trends, which work very nicely. A nice property of the jet is that the Reynolds number along the jet does not depend on z, and this is satisfied here. We have a Reynolds number R lambda which is of the order of 230, and the reason why this Reynolds number does not depend on z is you see that velocity goes as z minus 1 and scale goes as z. So when you calculate Reynolds number as sigma u multiplied by RE divided by the viscosity, the z dependence cancel and you have a jet that is constant in Reynolds number at all locations. Okay, so now we have all the ingredients to be able to stationarize the variables as proposed by Batchelor, and then calculate the Lagrangian statistics of these stationarized variables and see if this Lagrangian self-similar hypothesis makes sense. So that's what we have done. Now we move to Lagrangian statistics. So we take trajectories of particles, and we will investigate these trajectories at different locations downstream the jet. So to do that, we take here some statistics at different locations in different balls. And we will consider for each of these balls all the trajectories that pass through this ball. And we calculate the Lagrangian statistics for these trajectories passing through these balls at the different locations. So the thing that we are interested in applying for extending the Taylor theorem is the correlation function, the Lagrangian correlation function. So we do that by considering along the trajectories, the velocities at two different times. Now that's what is shown here. So this is the raw correlation function when we do not do the stationarization proposed by Batchelor. And you see that in that case, indeed, the correlation function is non-stationary in the sense that it depends on the position at which you measure it downstream the jet. Now, if you do that for the stationarized variables here, see that apart from the first location, which corresponds to this line here, which is for z over d equal to 15. So it's the measurements at the first locations, which are near the nozzle, so still in the near field region. The other correlation functions for the stationarized variable collapsed onto a single, almost onto a single line, showing that this Lagrangian correlation function for the stationarized variable has indeed reached this self-similarity, Lagrangian self-similarity that Batchelor had predicted. And you see that it works better as you consider further and further locations, because then you get to the real far field regime of the jet, where the self-similarity is known to be more accurate. Okay, so that's first hint that is interesting, saying that this idea by Batchelor indeed works. And now we can go a bit further by characterizing more precisely this correlation function. In particular, can we define the Lagrangian correlation time? So to do that, what we can do is to see if we can fit these correlation functions by a double exponential fit. So that's what we have done. It's shown here by this red line. We fit it by this simple double exponential coming from this simple software model, where correlation from stochastic models. And once you have these hands, it's easy to calculate the correlation timescale as the integral of this correlation function here. So we can calculate this TL, and it is plotted here. So actually what is plotted here is the inverse of TL. We'll understand why in a minute. But what is important here is to see that TL indeed tends to a constant that does not depend on the location, so that the TL for the stationarized variables, for these variables, stationarized a la Batchelor. So TL is indeed now independent on the position along the streamwise direction. So we are still satisfying this Lagrangian self-similarity hypothesis. Now we can go a bit forward and wondering whether this stationarized correlation, Lagrangian correlation time, does it fulfill the same usual relations that we know work relatively well for homogeneous turbulence? So in homogeneous turbulence, we know that the ratio between TL and TE is proportional to this constant C0. So C0 is the constant that appears in the Lagrangian regime, or in the inertial range regime for the Lagrangian second order super function, is one of the constants that is important in these stochastic models. So here, indeed, the stationarization procedure by Bachelor, TL tilde, the stationarized one, is directly TL divided by TE. So that's exactly what in homogeneous isotropic turbulence, this model tells us should be C0 divided by 2, where C0 again is this constant here that appears in the inertial range for the second order Lagrangian suite of functions based on Kolmogorov-41 phenomenology. S2 should be proportional to epsilon tau, and C0 is the proportionality constant here. So to estimate C0, we need to look at this Lagrangian correlation function, which is here. It's just the second order moment of the Lagrangian increments along particle tracks. And it is plotted here, S2 as a function of tau. So here it is plotted for the raw velocity, the non-stationarized velocity, and the inertial range appears in this regime where S2 is linear in time. So somewhere in this regime. So now if we plot S2 for the stationarized variables, U tilde, so that's what we see. So we see that apart from the first one here, which corresponds again to the first location, we're still in the near field, where we still have near field effects, all the inertia, the Lagrangian inertial range for the stationarized variables tend to collapse onto a single regime here, meaning that we can define a single C0 value for this regime. But what so self-similarity works nicely for this regime, for this range. But surprisingly, what we see is that for the small scales here, we don't reach this self-similarity. So what this is telling us is that C0, the constant for the initial range dynamics, gets independent of Z and satisfies this Lagrangian self-similarity. But in the small scales, we should expect that the constant A0, characteristic of the small scale, characteristics of the acceleration dynamics of the particles, should not reach self-similarity. And I will discuss this briefly later on. But the nice thing is that here we can estimate C0 by simply looking at the linear trend here. And when we do that, what we see is that C0, which is plotted here as the blue line, tends to a value which is roughly independent of the location, Z, the streamwise location, with a value of the order of 3.2. And 3.2, that corresponds here to, if you take 3.2 divided by 2, that will mean TL tilde of the order of 1.6. And amazingly, that's precisely what we measure when we measure TL from the correlation functions. So this is very nice, because it's telling us that all these ideas by Bachelor, this Lagrangian self-similarity, works really well. The Lagrangian correlation function reaches this self-similar regime where TL is not only independent of Z, but also satisfies this very simple relation here from homogeneous isotropic turbulence. So for this first part here of my talk, the take-home message, I would say, is this one, is that, regarding the Lagrangian self-similarity. So Lagrangian self-similarity holds, it works for S2, at least at inertial scales. Lagrangian self-similarity works for the correlation function. Hence, we can use the extended Bachelor theory for diffusion, and we can then use this extension of Taylor theory to describe the dispersion of particles in these non-homogeneous flows. I have not shown it here, but the self-similarity also works if you consider points not only in small spheres in the center line, but also out of the center line, so also off-axis. So this off-axis case was something that was not studied by Bachelor. So hopefully we can even extend this Bachelor approach to other regions of the flow, not only to the center line. We have also seen that the correlation, the stationarized correlation, is very well described by this simple double exponential model coming from, so what means that we can use this simple stochastic modeling applies even for this case of jets, if you consider the stationarized variables, and you retrieve then the usual relations, for instance, between TL, TE, and C0, and so on. So this is nice because it means that we can, for instance, use a classical model. So here I just wrote a very simple Lagrangian model, but we could use a software model or more sophisticated models with multi-layers, as we have been also working on for this kind of systems. But we can use a model as if we consider it for a stationary system, and then we just need to unstationarize the velocity u by unwrapping the formulas proposed by Bachelor once we have the result from this stationary model. So that's something we are doing now, and it seems to work really well and to give a very nice and very simple way to model the non-stationary dynamics from an initial model which is itself stationary, and you just need to unstationarize it with these very simple formulas. So a few things do not work, however. So things that are not working is what I was telling you, these small scales here, which are not stationarized properly by this procedure that we're proposing. So that we understand because we know now that our tracers are too large to actually resolve acceleration. And this discrepancy here actually is not really related to the jet itself. It's a finite size effect. Particles are too large, and we have a filtering effect of the actual acceleration of the flow due to the finite size of the particles. Another effect that I have not discussed today, but that is not working so well, is that these relations for homogeneous isotropic turbulence, as the relation with TL and TE, for instance, that I was discussing, doesn't seem to work so well if you consider the transverse component of the velocity. They work very well for the axial component, but not so well for the transverse component. And that's very likely related to the fact that when you see the nozzle, when you see the flow only through the nozzle, your statistics are missing the components of the entrained particles. And that's the other part of the talk which I would like to discuss. What is the role of entrainment? What is the role of these entrained particles that we are not tagging in our experiment on the overall process of diffusion? And what is the role of the mechanism of diffusion? So in this sketch here, what I am showing is just that these thread particles represent some particles that were in the outside part of the flow, in the quiescent part of the jet, get entrained in the flow, and then move forward with the jet. So in our experiment so far, we're only tagging particles coming from the jet. But the overall dynamics, the dynamics of the global jet, for instance, if you would measure the velocity with a hot wire, you put the hot wire, then you don't tag specifically some particles coming from the nozzle or coming from the outside part of the jet, you just measure the global dynamics of the jet. Then this has contribution both from particles coming from the nozzle and particles which have been entrained from the outside into the core of the jet. So in our experiment, somehow by tagging only nozzle-seeded particles, so only the green part here of the flow, we can somehow disentangle the role of the red particles that we are not tagging, because we know a lot already on how the jets behave for the total dynamics of the jet. So we'll use this idea of seeding only the nozzle of the jet to try to disentangle the contribution of the nozzles and of the nozzle-seeded particles and of the entrained particles. So to do that, let me first remind you very briefly what we know about the total jet. And you see that an important effect that can be expected from the entrained particles will be on the transverse velocity. The streamwise velocity is dominated by the velocity coming from the jet, while the transverse velocity will be strongly affected by the entrained particles. So if you measure the total jet, for instance, using hot wire, so here I took some measurements made in the 80s by Hussein and collaborators, you can, for instance, measure the axial profile. So this is the self-similar profile, F, the streamwise self-similar profile, which I already briefly discussed earlier as a function of the self-similar variable eta. So it resembles to this. And then you can measure the self-similar transverse profile of the velocity, which resembles to this. And again, I remind you that this has been measured with a hot wire. So you measure at the same time the nozzle and the entrained particles. You cannot disentangle which particle you are measuring in that case. So what is interesting is that in such a jet, if you are in an incompressible jet, the two profiles are related
by analytical relations related to incompressibility, meaning that if your flow is divergence-free, and if you have a self-similar jet, it can be shown. So this is a well-known result that you can find, for instance, in the book by Stephen Pope, that the transverse profile is analytically related to the actual profile by this simple formula here. So G is the transverse profile, F is the actual profile, the streamwise profile. So for instance, if you approximate the actual profile by a Gaussian profile, which is reasonable, you can use other approximation like a Lagrangian profile, but if you assume a Gaussian profile, then you can find analytical expression for this transverse profile. So actually, we did a set of experiments in our flow where we tried to put particles also in the outside part of the jet just to test these well-known relations, and it works well. So here you see the actual profile. The green line is just a Gaussian fit on this Gaussian profile, and here you see the self-similar transverse profile, and the green line is the one that you calculate using this formula, coming from simple incompressibility assumption of the jet. So this works well, but that was something that was known. So now we can do the same game by considering only the nozzle seeded particles. So we consider now only this green part here of the jet. So when you do that, you measure the actual component, which is almost indistinguishable from the one you measure when you have all the particles. But for the transverse component, you see that it is very different. So here the green line corresponds to the prediction if you assume incompressibility in these systems, the one that we have shown previously that was working for the total jet. But now the transverse component of the flow, if you measure only the part due to the nozzle seeded flow, is very different from what you would expect from the total flow. And the difference is due to the fact that here we are not taking into account the contribution from the entrained particles, which has not been tagged, or almost not. We have some spurious particles that are entering, but most of the particles that we are tracking were only injected through the nozzle. So what this is telling us is that in these flows, since this is almost equal to the original flow, but this is very different, we cannot use this usual relation due to incompressibility. What this is telling us is that actually the flow tagged by the nozzle particles is not actually incompressible. It has an effective compressibility. And the actual relation that must be used to connect F phi and G phi, so phi here refers to the fact that we only consider the nozzle particles, is not compressibility, but it's just mass conservation. What is the divergence free is the flux. Phi is the concentration of particles multiplied by the velocity u. And now if you derive the same calculations as in the Pope to get this expression, but instead of writing the divergence free of u phi, you write the mass conservation, then what you get is this very simple relation where the transverse contribution of the velocity for the nozzle seeded particles is also simply, much more simpler actually than for the previous case, related to the streamwise velocity f here. Okay, and if you assume a Gaussian profile, then you will get this expression for G, which is given here with this green line, which works very well for our data, except in this out region. And that's because this out region is very sensitive to the very few entrained particles that are still outside the jet and that we're getting in there. But what is important to see here is that the role of entrainment, which is the difference between these two lines, is very important up to the core of the jet. Even in the center line of the jet, you have a huge role of entrainment. In particular, the slope here of these two profiles. So it can be shown that the slope of this one is exactly 1/2 and this one is 1. So the contribution here is almost 100% due to the entrained particles. So if you put all this together, in the end, you see that when the relation for the global jet, that the one that I told you can get from the Pope book, is here. If you consider only the nozzle particles, you have this relation here. Take into account that F for the nozzle particles and F for the total particles, so the streamwise velocity are almost identical. You can rewrite this relation here for the total jet as the fact that the transverse component of the velocity is simply a simple addition of the contribution from the particles coming from the nozzle plus an additional term, which is here. And this additional term actually gives you exactly the contribution to the transverse profile due to the entrained particles. So we can rewrite this relation here and introduce this new term here, which we call zeta eta, which is a term which gives you the entrainment, we call it the entrainment term, and it gives you the contribution of the entrained particle, a global contribution of the entrained particles to the global transverse profile of the jet. You see the transverse profile of the jet, so this transverse velocity is the one that is related to the dispersion of the particles, so the transverse dispersion of the particles. So the next question that we wanted to ask is, then what is we can have intuition that this entrainment term will have a role in the span-wise dispersion of the particles. So can we relate this sort of entrainment, can we go forward and relate this entrainment term to the diffusion properties of the particles? And this can be easily done by simply adopting an alternative description. So here we describe the spreading of the jet, of the particles seated in the nozzle, as a contribution of the jet from the nozzle and of the entrained particles, which tend to grow to make this jet grow and the particle to diffuse. And we can also write this in a more classical way, which would be a simple advection diffusion description, where the velocity of the particles seated here, injected here at the nozzle, will be the velocity of the total jet plus some effect of diffusion, which is related to the turbulent fluctuations of the particle. And this can be written in terms of an advection diffusion equation here, where we have here the advection term and here the diffusion term with some turbulent diffusivity KT. Now, if we want these two descriptions to be equivalent, then you see that for the previous descriptions in terms of entrainment, we wrote this mass conservation here. So the divergence of phi, u phi was 0. And for the advection diffusion description, we have this other relation. So if we equate these two relations, that means that we can rewrite u phi as u minus kt multiplied by the gradients of phi divided by phi. Okay? So the two descriptions are strictly equivalent if we have this relation. Now we can rewrite this relation in self-similar variables, and that gives us this simple relation here for this advection diffusion description. And now if we compare this expression to the previous one that we had here with this entrainment term that I discussed before, we can see that the turbulent diffusion KT, well, that's the self-similar turbulent diffusion normalized by the value in the center line, is directly related to the entrainment term here. This is zeta. And this ratio of phi is the concentration profile of particles in the jet, and S is just the angle of the jet. So we can rewrite this diffusion coefficient here directly in terms of this entrainment term zeta. So this intuition that we had is correct. The diffusion coefficient can indeed be directly related to zeta. So time is running, so I will not go into much more details to this, but the nice thing is that this very simple approach can be extended, and we can find a very simple similar relation, not only for the turbulent diffusivity, but also for the turbulent viscosity, nu t, and eventually for the turbulent Prandtl number, nu t divided by kt. Beyond the connection that this makes between diffusion and transport coefficients and entrainment, the nice thing is a very practical interest, because here you see that you can determine these quantities, these transport quantities, turbulent transport quantities like K or nu, turbulent diffusivity or turbulent viscosity, by simply measuring these very simple quantities, which is the profile, the mean streamwise velocity profile F, and eventually the mean concentration profile phi of particles. But you do not need to measure stress tensors like usually when you want to determine viscosity, eddy viscosity, for instance. You just need to measure these very simple mean field quantities, and that works. We were able to measure not only the mean value of K, but really the profile, the spatial non-uniform profile of these diffusivities and viscosities. Okay, so I will stop here. So for this last part, what is important to take home as a message is that entrainment finally does not affect the streamwise dynamics of the particles. It mostly affects the transverse velocity profiles, and this can be written as a new term that is an entrainment term that is defined here, and that this entrainment term then directly allows to estimate turbulent transport coefficients by only measuring these simple mean field profiles. And while of course this work has a lot of extensions that we are working on, but I will stop here and thanking you for your attention. Thank you.
Thank you, Mickaël, for the presentation. So I would say we can start with questions. We have some questions in the chat already. Maybe we can start by replying to them. I don't know if you want me to report them or if you want to read them by yourself.
Okay. If you have questions, I'm ready to take them.
Yeah, so the first question is in the discussion. It's like, is the turbulent jet in quiescent flow or turbulent jet in another turbulent field?
Sorry, Francesco, I had a speaker problem.
Do you want me to repeat the question?
Do you hear me?
Do you want me to
okay.
to repeat the question? If
yes, sorry, I don't know why my speaker just stopped. So please.
Sure. So the question is it are you considering a turbulent jet in quiescent flow or a turbulent jet in another turbulent field?
Yes, no, sorry. Here the jet is injected in a quiescent flow. I mean, almost quiescent. The jet is small, the vessel is large, so there may be a very small recirculation that we try to measure, but it is orders of magnitude smaller than the jet itself. So we consider the surrounding flow to be quiescent.
Okay. And I think there is another question in the chat that was somehow explained in the presentation, but maybe it's good to repeat it. Will R2 Lagrangian always show a non-zero correlation even after a long time?
So you mean if the Lagrangian correlation function goes to zero at long times? Yes, I think it should. It does.
Okay, that's okay. So these were the only questions reported in the discussion. So maybe we can now pass to the question from the audience. Please go ahead.
Hi, hi, Mickaël.
Hello.
This is one. Thanks for the great talk. Really interesting.
Thank you.
So I was wondering about the first part of the jet, where the self-similarity doesn't seem to work very well. So, like in overall, thinking about all of this kind of Lagrangian scaling, like what's the philosophy behind this? So basically, the fact that we can rescale correlation functions, time scales, etc., based on the position of the Lagrangian particles, like inside the jet. So would it be equivalent to saying that Lagrangian particles, well, at least far away enough from the jet nozzle, don't remember their history anymore, and that you know the dynamics is determined only by what they see locally as they go along the jet, and then like maybe this could kind of an argument like could explain what happens near the nozzle of the jet. Do you know what I mean, or did I?
So I don't know if we can really say that they forget what is happening, because finally the profiles that we use to rationalize them are built by this history of the particles, of how it decays. I mean, it decays in a certain manner, right? So I mean, the fact that these profiles, for instance, decay as 1 over z, you can rewrite it as a function of time, right? If you take the distance particles travel on average, so you can rewrite this as a function of time. So you still have, I think, encoded in these fields. That's probably precisely why that works, because we have encoded in that fields the entire memory of the path.
Mm-hmm. Okay, so basically it relates to the fact that we have a scaling for the length scale or something like that, and that the mean usually the particles go along the mean flow, which is in the center line. I mean along the axis of the jet. Do I understand it correct?
Well, I mean, here in Bachelor's approach, let me just go back. If you read Bachelor's paper,
yeah,
he'll only do this stationarization here by considering the z location. So he will mostly work only in the center line or near the center line. Yes. What we did here, I mean, I didn't detail it, but we tried to do it a little bit more general. So if you do the Bachelor thing in the center line, that works pretty nicely. But what we did was really to use the UI of X. So actually, we didn't even use the measured, the fitted profiles. We really used the measurements to stationarize this, taking into account, as you see here, not only the decay in Z, but also the decay, the radial decay here. When you do that, so the results I showed, let me see, I think I have a hidden, no, but if I quit the presentation, we lost the sharing. But we did a set of measurements. If you take not these spheres that I were showing you, okay. If you, instead of taking the measurements here, you take them along a line that is here off center. So that's a case that we didn't consider. When you do that, it also works. It also works quite nicely. Mm-hmm. So my intuition is that this stationarization should be probably more general than just the decay in Z, right?
Yeah. And, yeah, so this is probably attributed also to the fact that you really take the position of the particles itself and taking that. But interestingly, I think in a recent work that we did using the measurement that we did from the canopy flow measurement that we have, we also saw the particles, I mean, really do have a turbulent strong component, and that I mean similar things to basically what you're discussing here. And then we kind of hypothesized that the reason for that could be a strong that the acceleration of the particles was basically stronger than the change that they experience as they traverse along the flow field. So maybe it could be also interesting to your measurements as well.
We also measure acceleration, but we have realized that unfortunately the particles are too big. So we are having a lot of filtering effects. We probably need to go much further downstream or use smaller particles and repeat the experiment.
Yeah. Okay, thanks.
Yeah.
Hi, Mickaël. I have a quick question.
Yes,
can we go back to the slide? I think you had the slide where you show the Lagrangian correlation function for, yes, that one.
Yes.
It's interesting. You don't show beyond one. I am thinking you don't show them beyond the tau tilde equal to 1.5.
Yes.
I was thinking that.
That's we don't have long.
Go on.
No, I was saying that's mostly because we don't have tracks that are long enough.
I see, because there are shear layers on the sides of the jet which give rise to coherent structures.
Mm-hmm.
And that might mean that for a while, as you go downstream, there may be an oscillation in the particle, in the fluctuations of the trajectory, which would appear on the Lagrangian transfer function, on the Lagrangian correlation function, as an oscillation around 0.
Mm-hmm.
If you integrate that oscillation around 0, it can give a much different, yes, and also a different diffusivity and so forth.
Mm-hmm. Yeah, that's a good point. I mean, the trajectories that we are seeing now, they definitely don't go that far. They stay near the center. That's mostly due to the tracking limitations. We haven't done it, but we could also look at, as I was saying to Ron a minute ago, to do similar analysis if we go closer to the boundary. That we haven't done.
Yeah. Actually, this oscillation I'm talking about may also be present near the boundary, but as you say, you don't have long enough trajectories to perhaps see it.
I mean, we don't have tracks that are long enough, like to explore the center and then go to the side. Yeah. Usually, we have tracks that is due to the tracking. Having long tracks is complicated. Maybe we could do that in numerics.
I mean, another way to put what I'm saying is that these coherent structures can trap actually the dispersion rather than promote it. And this can be seen by an oscillation in your correlation function. Thank you very much, Mickaël. Thank you.
Thank you, Christian.
So I see that there is also another question in the chat. So why the entrainment affects the self-similar bachelor analysis if it's still self-similar?
Yes. So we refer probably to the to this last point that I was pointing here. So actually, that's also something that I haven't shown. But if you do this analysis for the radial component, the transverse one, the self-similarity works very well. So yeah, that's correct. I mean, everything is self-similar, and that works very well. What doesn't work so well is the time scale. So what I've shown here is the time scale for the radial component, and it's very, very different than the time scale for the streamwise component. So that's what I was saying, that it can be a role of maybe a role of this part of the flow that we are not measuring. So the radial component still fulfills this very nicely. This self-similar Lagrangian dynamics is just that the details of what the Lagrangian time scale is, what are the other magnitudes that are a bit different compared to the streamwise component. So in that sense, we still keep this Lagrangian self-similar dynamics, but it's not so isotropic. So one of the hypotheses is that it could be a role of entrainment. It's not. I mean, it cannot be conclusive here. We would need to repeat these measurements, having particles everywhere and compare the situations. But that's what I meant. I don't know if that answers the question.
Yeah, we have the reply that's in the chat. That's yeah, that's okay. I mean, that answers the question. Is there something else? Someone else who want to ask a question? Please just feel free to unmute your mic and pose the question.
Hey, Mickaël, if I may drop and ask a question. Thank you for the presentation about the Lagrangian correlation plots I think in slide 37, I guess. Well, we say when we do a stationarization and we try to see self-similarity, we see in the inertial range, and its inertial range we say from the it varies between Kolmogorov to integral lengths, right?
Mm-hmm.
But from the measurement, we don't have the measurement between with the size of Kolmogorov time scale. We let's say this is the inertial range that we have from Kolmogorov to integral scale. We usually vary in this region, and we don't have such a small scale acquisition. I don't know.
Maybe that's easier to see in the Stutter function plot. So, which is roughly equivalent to the correlation. So here, what you see that the inertial range is somewhere here. In this. And what we would see as dissipation, which is here, well, in our case, actually the cutoff is probably very much related to the finite size of the particles rather than the actual dissipation, because the particles are not so small. I mean, we thought at the beginning that 250 microns would be enough, but actually 250 microns in almost all the experiment is still of the order of 10 to 15 dissipation scales. So this cutoff here is probably due to finite side effects. So what we mostly resolve is the inertial range. Clearly, we don't see the large scales because of what I was saying to Christos, that we don't have
trajectory lengths
that are long enough. But the small scales are sufficiently well resolved. I mean, the repetition rate and the noise efficiency is low, so that we do resolve the small scale of these particles, but which is a filtered acceleration dynamic compared to what the flow would be. So that's,
you mean you filter the lengths of trajectories that you compute the autocorrelation and structure functions, right? The lengths of tau in, for example, in this in S structure second order structure function.
Yeah, tau, the smallest tau is just given by the sampling rate. I think we filter a little bit, but very little. We filter on 2 or 3 frames. There is very little noise in the data, but that's also related to the fact that we have this physical filtering due to the finite size of the particles. So the acceleration of our particles is actually lower than the actual acceleration of the flow because of this finite size effects.
I see. And another. Oh yeah.
I mean, that's probably why we don't see this self-similarity for the acceleration. So it would be nice to repeat this experiment with smaller particles to see if we do reach this Lagrangian self-similarity for the smaller scales.
So we can say it's valid for basically the second part of the, if we say this is inertial range, for the mostly larger scales of the inertial scale, it's valid. We cannot, we can say it's, well,
at the moment, we cannot, with our data, it doesn't seem to work at the smaller scales, but I don't see why it shouldn't. And so I really think if we this experiment with much smaller tracers, I suspect that this will work in smaller scales. And we need to check.
Yes. And how do you quantify the sphere size for the Lagrangian statistical? How do well, if the case is not the jet, like it's another self-similar case, how do we quantify this one?
Sorry, how do you quantify what?
The sphere size to compute the statistics on the left of this.
So what is important is the ratio of is d over eta, right? But in this flow, eta evolves with the streamwise direction. So when the particles are very near to the nozzle, eta is actually very small. So our particles are gigantic. I mean, d over eta in the near field, I think is close. I don't have the numbers in mind, but it's probably above 20, 25 probably. And as we consider further directions that are further downstream, eta grows linearly with z. So in these regions, d over eta gets smaller, but it's still of the order of 10. So that means that the particles are still much larger than eta. For acceleration to reach something that would behave as a tracer, I mean the thumb of rule is that d over eta should be below 5 or of the order of 5.
I see.
So in our case, they are still too large to hope resolving acceleration.
Okay, understood. And one more, the last question about the C0 computation. I know it's somehow Reynolds dependent, but the value, for different case, for different self-similar case, how do we say the C0 is valid, or it's
so in our case, we measure something of the order of 3. I think I have here a plot.
Yes, it's 3.3, I guess.
Yeah, so I have here this plot. I think this one is from the Sofford paper, which gives you an estimate of C0 as a function of R lambda. I don't know if you take 200, according to this plot, is something near to 4. So 3 is reasonable, I think. I cannot. I mean, we would need to review. I mean, there are much recent values of C0 than this one by Stofford, but I think that a C value of, if I would have found like C0 equal to 300 or 10 to the minus 2, I would be worried. But I mean, 3 is a reasonable value. So I don't know if it is exactly the same value as in homogeneous isotropic turbulence, but it's at least consistent with usual values of C0 at this Reynolds number.
Okay, understood. Understood. Thank you.
You're welcome.
I actually have a question related to the previous one, just to the previous slide, and it's yeah, to the S2L, because yes, that's it. So when you said that the S2L actually the correlation is supposed to work also for small tau tilde, and you say, okay, the curves kind of diverge from each other because the particle size has an effect on the statistics. Just to understand it better, so why should they deviate differentially, taking into account that you have the same particle? Is it just related to the fact that the particle basically can be considered like a filter to the measurement, so it works like a low pass filter kind of thing, and this low pass filter actually counts more when you are close to the nozzle, because basically like your profile is self-similar, but the particle does not scale self-similarly, so it counts more at the beginning than at the end, something like that.
That's exactly the point. I mean, when we measure, for instance, in homogeneous turbulence, we measure a lot acceleration. When you vary the size of the particles, we see that the acceleration that you measure, let's say the variance of acceleration, which is what gives you this regime here, is related to sigma A squared. This one depends on d over eta, the ratio of d divided by eta. And so in homogeneous turbulence, for instance, you keep eta fixed, you change d, and you see how it goes. In this case, it's the other way around, exactly as you said. The size of the particles is fixed, but as they move along the jet, eta is changing. So the d over eta is evolving along the trajectory. So, and that's probably even more complicated than when you really just change d over eta in a fixed flow. So the dependency that we see here seems even to be stronger than what we measure in a homogeneous isotropic flow when you just vary d over eta. But we clearly see this effect that the acceleration strongly depends on the ratio d over eta. But it's exactly what the size is constant, but eta is evolving.
Okay. And just to follow up, do you think that this can kind of explain why the purple curve does not match the rest? Because I mean, the closer you are to the jet, the more like particles who are blown in the system, they kind of start having two effects. One is the particle is bigger compared to the, so it filters more somehow. And on the other hand, also you are blowing a lot of particles, so particle-particle interaction there provides another source of kind of resistance to the particle flowing with the fluids. So can this somehow explain why the purple curve kind of gets far away from the other three curves? Or
Yeah,
it's really like inherent to intrinsic in the flow?
No, I mean, it's a good point. That's true that in the system is relatively dilute in particles, but near the nozzle is 4 millimeters, and the particles are 250 microns. It's a quarter of millimeter. So that's why it's not so small compared to the nozzle. So it can also be that if you release several particles at the same time, you have some local modification of the flow in this region. That's a good point. We haven't really explored this question. I think it would be interesting to repeat this really with much smaller tracers. But then we need a stronger illumination, and it's a bit more complicated. But there are several points, as this one, as you pointed, that would be nice to clarify. Yeah, so I don't have a clear answer. It's probably a problem of near field, so self-similarity is not so good, but indeed we can also have stronger couplings in this region.
Okay, and just one last follow-up on this. You talked about the entrainment, and how does the entrainment is going to depend on the distance from the nozzle. Like I expect that it's not scaling really similarly with respect to the distance from the nozzle, right?
Well, so what we see, for instance, here on for the transverse profile is that the contribution of entrainment is really given by, let me go, okay, by this term.
Yeah.
So, and here eta is R over Z. So it's really the self-similar variable. So it really seems that the entrainment contribution also satisfies this self-similarity. Yeah? And
but the tail of the curve didn't seem totally well predicted by this model.
This part here.
Yeah.
Yes. So our suspicion is that this part, because you see here, this part goes a bit negative.
Yeah.
While we are injecting the particles only in the nozzle, and actually this part eta equals 0.3, 0.4 is really far actually. Is somewhere here. So our belief is that this part is dominated by some pollution of some particles that are actually entrained. That it's not really nozzle-seeded particles. So it's what I was showing at some point at the beginning. Let me go backward rapidly. Okay, there, here. Yeah. So when you start really looking at statistics very far away, I think we are dominated by pollution from these particles, which have indeed this negative radial velocity.
I see.
It's very hard to remove all the particles in the outside. You also have some that remain. Sometimes we filter and filter for hours, but you still have some.
Yeah, maybe you get also a measure recirculation.
We have a little bit of circulation that also know. Yes.
Okay. Thank you. Thanks.
You're welcome. Thank you.
Then let's see if there are other questions from the audience. If there are other questions, just feel free to unmute your mic and ask a question, or just write in the chat and I can report it. Well, that doesn't seem to be the case. So thank you once again, Mickaël, for the presentation. It was really interesting, and it raised up a number of questions. So
thank you very much. Thank you for the invitation.
Thanks again. And so I just give a couple of announcements. So I forgot to write in my mail that the webinar of Stefan Zaleski, who was given last week, has been uploaded yesterday on YouTube, and this webinar will be uploaded in about a week. Then I hope to see you all next week once again. Have a good evening.
Thank you, Francesco.
Thank
you all. Bye bye.
Bye.